Okay, and then okay, I think okay, and can you share again?
Yes.
Okay,
Can you see my screen?
not yet. Yeah, I can now. Yeah.
Okay. So, in this question, it's actually, I think it's pretty straightforward,
Hmm.
but it just asks you to compute the sum if it's greater than 10.
Okay. Yeah.
And I'm seeing right here that the root is 19.
Yeah.
So then the thing, okay, so what makes it different is if I have 19, I know that everything that's less than 19 goes on one side and everything that's greater than 19 goes on the other side. And since 18 is less than 19, but it's also greater than 5, that's why it makes sense for it to be right here. But then suppose if you had a root that was like 4 or like, yeah, 4, then is 18 still allowed to be there? Because it's technically less than 4, but it is greater than 5.
Uh, yeah, so you're right that it needs to be greater than 5. So 4 could not be in that position.
No, but like if the root was 4, then is 18 still allowed to be
So
there?
you mean if it was 4 instead of 19?
Yes.
Then it's not even a question of 18 because both 5 and 20 are greater than 4. So 4 could not be the root.
Or I'm sorry, what if like 6 or 7? Like something that's um
Uh,
greater
then
than 5, but
then
also
yeah, like anything between 5 and 20 would be allowed. And then but then yeah, so 5 would be okay. However, you're right that everything to the left of the root needs to be smaller than the root. So 18 would not be allowed if the root had been like 9 instead of 19.
okay, so then in that case, is it okay if when you have the root and if you know that the root is just 10, then is it okay if you just look at the right side to compute
Yeah,
the sum?
yeah, yeah. So, and I think so yes. If you see that the left child is, I guess in this case, smaller than 10, then you can just return 0 right away. Now, you do have so this is not kind of super useful for this question because you do have situations anyway, right, where it might be that 5 is not does not count, but it has a child that does count,
Yes.
right? So that kind of means that probably the best strategy there would be to just return to add 0 if the number is smaller than 10.
Okay, got it. Okay.
So so like you're right though that like if you're looking at whether to go to the left child and the left child is already small and then so yeah.
Okay, got it. Okay, that was like my main question.
Yeah.
Thank you. Um, Also, could you go over question in the 2020 exam? Could you go over question 5, please?
And
Or the
20
2021 exam?
midterm was question 5 not excluded? Guess it wasn't. Um, okay. Okay, so let me just reacquaint myself with it. So we have distance between two lists. Sorry, let me share. So we have distance between two lists, and the distance is the number of transformations required to transform one list into another, right? The way it works here is we go, sorry, I'm just reading. I haven't read it in a long time, even though I wrote it. So the distance between 1, 1, 2, 3 and 2, 2, 3 is 2 because you can remove an element and then you can substitute this 1 with a 2 and you get this. So the elements are given in particular order. So what we want to do is we want to define it to the array, and we want to compute the distance between L up to I and L up to J. So this is, I guess, a typo. So this is like L1 up to I and L2 up to J. And the distance to the empty list is I because to the empty list from something up to I, so like I elements is I because what you need to do is you need to remove all I elements. So for example, the distance from this to the empty list is 3 because you need to remove 1 and remove 2 and remove 3. Okay. So the first one is so we are computing we're computing the so we're computing just this kind of thing. Okay, this is like the whole thing. So we are constructing the array, which is just all the distances. So okay. So we'll say, okay, so this is we'll initialize the to all zeros. So so now we'll use the fact that the distance to the the distance to the empty list is just the length of the source, right? So distance L1 to I and empty is I. So we do it like that. Does that make sense?
Not really.
So
Like I get where you go. I get how you say
yeah.
I equals 2, 0 times length, 2 plus 1, but then why do you say that distance?
So I'm just saying like the distance between the empty list and this is I. The reason is that if you need to remove I elements one by one, that's a distance of I.
Oh, okay.
Right? And then I'm writing it down as I'm going to compute the distance. So this is the distance between L1 up to I and L2 up to 0.
Okay.
Is that okay?
But why 0?
Because so this is like the thing that they know how to do right away, right? So I'm eventually want to be able to compute the distances from everything to everything. But what I know as the base case is if I take a chunk from L1, so everything from 0 and up to I, the distance from that to just the empty, which is, so empty is like L2 up to 0, right? That I know. That's I,
Okay.
right?
Okay.
And similarly, the other way, so the distance from the empty to L2 up to J is just J.
Okay.
Okay. So all right. Now that we have this, we want to kind of we want to move on, right? So we basically need a recurrence, right? So how can we compute the IJ if we know the answer for smaller i's and smaller j's, right? So the idea is kind of like this. So if I know that, so suppose the distance from L1 up to I minus 1 and L2 up to J is D, right? So then the distance from L1 up to I, L2 up to J is at most D plus 1, right? Because what you can do is you could just say, okay, like in order to change this into this, I need D. So that means that what you can do to go from here to here is just remove the extra thing at the very worst, right? And then go from here to here. Because if you remove the last element from L1 up to I, you get to here. And in order to get from here to here, you need these steps,
Okay, that makes sense.
right? So that's kind of the idea. So in general, what you would say is so what is this? It's kind of like go through all the possibilities, right? So one possibility is what we mentioned above, like D plus 1. Another possibility is that the way to get from L1I to L2J is to insert an extra element. Another way is to substitute one element into another element. And those are like the three ways, right?
Okay.
Does that kind of make sense?
Yes.
Okay. So then like what we do is we just kind of keep computing Dij, right? So the situation is kind of like this. So if it happens that L1I minus 1 is the same as L2J minus 1, then the distance is actually just the distance from L1 up to I minus 1, L2 up to J minus 1, because the last element is the same. We don't need to touch it. All we need is to just like take care of the other elements, right?
Um, okay. I don't know
So
if I'm like messing something up, but isn't it like when you go from I minus one to I, you're adding one? So then how can you say that I and J is the same as I minus one and J minus one? Because
the situation is kind of like this. So imagine that the strings are like A, B, C, Z, and like D, E, F, Z, right? Then in order to go from here to here, what you do is you just don't touch the Z, right? Because it's already in the correct place.
But then how can you say that D of I and J is the same as D of I minus 1 and D of
Well,
J
because
minus 1?
so think about it like this, right? So like let's say that this is L1 and this is L2, right?
Okay.
So then we say, okay, so the question is how many operations we get from L1 to L2, right?
Mhm.
And what we're saying is if L1 3 is equal to L2 3, then it's the same as the number of operations we get from L1 up to 3 to L2 up to 3.
Okay, that makes
Because
sense.
the Z states, right?
Got it.
So yeah.
But then are we kind of assuming that for each letter you're only gonna have like one transformation happening to it?
Not really. It's so it's just that if you substitute the same letter more than once, then it's not the most efficient thing.
Okay.
Yeah. So here I didn't initialize D, I think. So so here we have like D, so we have like D at I, so we need to have something like this initially. So okay. So yeah, that's basically it. We return D. So then the next thing is
I'm a bit confused though.
okay.
Like in the test case, it says like if you go into the question, the
Yeah.
test case says 1, 3, and 1, 2. What is that implying? And how do you get 0, 1, 2, 1, 0, 1, and 2, 1, 1 from that?
Okay. So the rows and the columns are kind of what we discussed, right? So in order to get from the empty list to the empty list, there's no substitutions, nothing is needed.
Okay.
So this is getting from the empty list, so from L1 up to 0 to just 1, right? So this is 1 and this is 2, because in order to get from this to from the empty list to 1, 3, you need to add 1 and then you need to add 3.
How do you know we have an empty list?
Because that's what the row means, right? So the first row is the distance from the full L1 up to L2 up to nothing, which means the empty list. Right? So that's like D0, the other way actually. So D0J, so for example, D02, so it's this guy. It's the distance between L1 up to 0, which means nothing, the empty list, up to L2 up to not including J.
But then wouldn't that just be J because of our base?
Yeah, and that's what it is. So that's why it's 0, 1, 2.
Oh, so we're just taking, okay, cool, got that.
Yeah.
But then shouldn't there also be something that says 0, 1, 3?
No, it's like it's counting the number of characters, right? So like this is like 0, 1, 2, 3, whatever. Like in this case, L1 and L2 are of length 2. So it's like from 0 up to 2. And
Oh,
then it's 0, 1, 2 this way as well.
okay. But then what about 101?
Uh, well, so the only way it works, I think, is with just zeros. So like those things you need to actually look at in detail, right? So for example, let's look at the 0 here. So the reason it's a 0 is because that's the distance between a list that contains 1, so like this one, and a
Mhm.
list that contains this one. So they're already the same.
Okay.
So that means that they're distance 0.
But then when you have to go from 2 to 3, you have to add 1, so that's one transformation.
That's so there's no going from 2 to 3, but if you need to go from, so here we are, so this is uh going from 1 to 1, 3. This is this one. So to go from 1 to 1, 3, you need to add the 3.
Okay, that makes sense.
Okay. And then so similarly, well, not similarly, but so in order to go from 1, 2 to 1, 3, you need to substitute the 2 for the 3. So that's why the 1 here.
Okay. Okay, that makes sense. So you're just going from like one. Oh, okay, wait, no, wait, that makes sense. So the first column is like you're going from one to the empty list. Then the second row, first column is like going from um the like from one to the empty list. And then like the second column is like you going from like one to one. And then the third column is you going from one to like the whole list to
Mhm.
a whole nother list.
Well, so the call, so that's the row, right? So the row is going from 1, 2 to first the empty list, and then just the first element, and then the first two
Both of
elements.
them.
Yeah.
Okay, that makes sense. That makes a lot more sense.
All right.
Yeah.
So okay. So that's the distance. So now we want the length of the shortest sequence of transformations from L1 to L2. So this is just this entry here, right? So you construct the distance thing, and then you return the bottom right corner.
And the reason it's the bottom right one is because you're looking at two lists, like
Well,
together.
you're looking at the distance between the two full lists, right? So
Okay.
like the distance between L1 up to the end and L2 up to the end. So that's the bottom right corner. Yeah.
Okay, that makes a lot of sense. Yes.
All right. Okay. So now we need like recover path. So there's like multiple ways of doing this. I guess we'll do it with the constructed D. So we'll construct the thing. And then we'll start with the end. And the path, so the path is like this. So basically what we want to do, so if I look at if I look at the distance matrix here, right? So if so here the distance is 1, right? And then going anywhere so I can go here, I can go here, I can go here, right? I want to eventually go to a 0 because like if I got to a 0, then I'm done, right?
Because your lists are the same.
Because the lists are the same. So so what they mean by like going from here to here is I'm saying, okay, like so I could have gotten from L1 up to 1 to L2 to just L1 and L2 by adding one element to L1. Right? So like going from here to here is adding, going from here to here is subtracting. I could also remove the last element from L2 and basically get from this situation to this situation. Right? And then I could substitute, and this is going from this situation to this situation.
Wait, how do you know, or is this just how um this kind of algorithm works? But how do you know that when you have to substitute, you go diagonally, when you have to um like delete something, you go
Uh,
like up?
well, because that's kind of how this matrix is constructed, right? So
Oh,
so and we're just talking about the last element, right? So if I'm so if I'm like going from here to here, then that means that I removed the last element from L1,
okay, cool.
right? If I'm going from here to here, that means that I removed the last element from L2. And if I'm going from or so like if I'm starting here, then it's remove. If I'm going from here to here, that's add. And if I'm going here, then that means I've substituted, right?
Okay, got it.
Uh, so the only thing is the substitution yeah, so the only thing is yeah, so that's like this. So where so here what we're saying is, okay, so which way are we going? So we're saying, okay, we're starting at the end, and get this out. So we're saying, okay, so if Dij is the same as going, sorry, so I said substitute before, which is wrong. So if the distance remains the same, if we keep the last element, that means we should keep the last element. So we'll just say we're keeping the last element, and we're going to find the path from L1 up to I-1, L2 up to J-1, right? If it's the situation that the distance remains the same, except with +1, if we had added the last element to L1 up to I-1, that means that that's what we need to do, right? So this is of L1. This is one of L2. This is L. Okay. So the logic here is if the distance, so if we can move to the left in the matrix and the cost is 1, then we do that. If the cost is consistent by inserting at L2, we do that. Otherwise, we replace.
Mhm.
Yeah. And then, so because we're constructing the path from like the bottom right, we need to revert it.
Okay. Which is why we have double colon.
I mean, this is like, if you remember, this is like reversing the list.
Yes. Cool. Okay, that kind of makes sense. Okay. Also, if you don't mind, could I ask you like a few more small questions? Um, First of all, do we need to know about what level ordering is?
No, I haven't mentioned.
Also, I can't hear you too well.
We have not mentioned that. No.
Okay, cool. And second of all, did we learn about how to implement the traversals in or like the traversals and also creating a graph in C? Because I'm looking back at most of my notes and we did them almost all in Python.
It is so. So two things. The traversals. So depth first, breadth first are referred to as graph traversals. So those we definitely had done. I think you might be asking about like in order, post order traversals of trees, which we had not done. So there is like.
Have we mostly done them? Have we done them in C a lot?
Yeah, we had not done them in C. We had implemented the graph in C the once, as far as I remember, maybe in lab 7 or something, right?
Oh, yes. Okay, yeah, in lab we did.
So yeah.
Okay, cool. So I'm assuming that like for an exam we might not have to do traversals in C.
I don't think that's a fair assumption because this is like what you could be asked to do an algorithm that you hadn't done in lecture at all, right?
Wait, then how would you I'm confused because I know in breadth first traversals and in depth first traversals, like you have the stack and you have like a list and everything, and you have to like pop or you have to push or you have to do something. How does that work in C? I'm not too sure I would know how to implement it. Like, could you go over a quick example?
Sure. So So you're right that you would need to kind of keep track somehow of keep track of nodes somehow, right? So you might need to like implement something like a stack, right? So to do that, what you could do is you could say, so like essentially what I'm doing is just a list of pointers to node that I might need to resize, right? So this is like the usual array list thing, right? So to create, so usually we're doing it like this, right?
Okay, so this is us creating the stack.
Yeah.
Also, why did you choose to do it as a double pointer? Because I know from like
Uh,
previous examples, we've also used single pointers for data or like no.
well, because what I want to do is I want to pass a point. So from outside, what I want to do is I want to say like node stack, and then when I'm creating it, this by the way is void now. So here the autocomplete wanted to just return it, but what we had done in class usually is we passed the address of the stack to the function. And then you're modifying the value of stack by sending the pointer to it to create node stack, right? So inside of here, start the stack is the same as modifying the stack outside.
Okay.
All right, so here, so push would be, like this. So
Yeah.
here we need to like increase the capacity and realloc whatever, like what's error checking, we'll do error checking. And here we're putting the node n over here.
Okay.
And then pop, we return, so this syntax we hadn't done, right? So I guess we'll do like node ret val is like this. And then we'll decrease the size of the stack and we'll return ret val. So now you can push and pop nodes from the stack.
Yes, but how would we use that for like a traversal, like for
Yeah, so like we need to like first create the graph, right? Uh so
but aren't we usually given a graph?
I mean like defined usually. So like we need like to do something, right, with So like we need like the neighbors and stuff. Like it's a little bit annoying to do. So maybe the node is like this, right?
Right.
And then we now need like a create node. So this is like the same kind of, are you okay with this?
Yes.
Okay, so we have the create node, and now we can do like an add neighbor thing.
Wait, so okay, this is like a silly question, but then
Mhm.
on an exam, if you're just given a picture of a graph, do you have to actually create the graph afterwards, or like when you're writing the code,
I
or
mean,
do you just do the
that could be
DFS?
a question like in lab 9, right?
Um,
Or like it could be that the point of the question is for you to like create the graph data structure, or it could be that I'm telling you like this is the graph data structure that's given, or like somewhere in between when I'm telling you like make graph data structure, but there are like this and that constraint.
okay. Okay, got it.
So yeah, okay. So we have like the add neighbors. So here, like it works the same way, right? So like the neighbors is uh an array of nodes, and initially the number of neighbors is 0. And
Okay.
then if we add a neighbor, we need to like reallocate with a larger number of neighbors. So okay. So let's create a graph. So we'll do like so here I think the neighbors are so the values are like integers, so it would have to be something like, so maybe the graph would be like this. So that kind of worked out for me, right? So here I created the nodes like on 0 and 1 and 2 and 3 and 4 and 3 and 4. I connected and 0 and then 1, and then I connected and 0 and then 3, and connected and 1 and then 2, and then I connected and 3 and then 4. Right? Does that make sense?
Yes, that makes sense.
Okay. And so now I have a stack, so I can do DFS. I'll create the stack, and I'll put the starting node. Oh, that was good. Um, so I like create the stack, and then I put the first node in the stack,
Okay.
and then I keep popping nodes from the stack and pushing every neighbor to the stack.
Okay, cool. Wait, that makes sense.
Mhm.
Okay. Okay, that makes sense. So every time I have like a DFS question, I need to, if it's in C or in like Python, I guess I need to like start off by creating the graph and the push node and everything, and then
I
I can
mean,
create
whether
the.
you need to or not. I also like, I think you're thinking about like one specific kind of question, which is like, here's a picture, like make code that does DFS. And by the way, DFS does not require an explicit implementation of the stack, right? Because you can do it recursively. So here it's just because you asked for a stack. But yeah, like if you have a picture of a graph and you want to like create that, yeah, like that's what you would do. Yeah.
But, how exactly does like the how does DFS recursion kind of work? Because I was looking at the lab or like the exam question that you sent where you tried to use like where I think you tried to use um recursion and it made sense mostly. Except
Sorry, which question are you talking about? Are you
like
talking about
question
like
6 and
Q5 or
7
something? Oh, okay, yeah, yeah.
for
Yeah, 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 yeah. Yeah, sorry. So what was the question?
how did you use DFS recursion in that? And also, if you're using DFS recursion, and my assumption is you're going to use DFS recursion so you can access the neighbors and then keep on accessing the neighbors,
Mhm.
how will you be able to go back to your original node once you exhausted that like line?
Right. So wonder if this is on this computer or not. Probably not. Okay, let me just get the code from Piazza because I think I did it on my other computer. So we're talking about this question, right? And I think what you're asking is like let's say that you're here, like
Mhm.
don't you need to like kind of track back to zero in order to know what's going on at all, right?
Yeah.
And the answer is the way the information propagates back is via return values. Okay. So
Oh, so
here,
is it kind of like those like Fibonacci type of things where you
yes,
kind of keep on going until you're at the very end?
exactly. That's exactly right. And that's like what DFS is, right? Is like you're going from here to here to here up until 21. And then once you got to 21, kind of 21 returns information. So for example, it returns the fact that you've reached 21. And then the question is like, what does 20 return? And then like what does 19 return? What does 18 return? And so on. So the way that the information propagates back is when you call is winning position with position equals 0, that calls this guy, and then it waits for this guy to return a value. And that's how like this, so the information about what happens at 0 is propagated back until you return from is winning position 1.
Okay. Then when would it be easier to use DFS recursion versus DFS stack? Or is it just a
Um,
matter of preference?
so I mean, again, like those are just like set algorithms. Like I would say it's like always, at least to me, more intuitive to implement it recursively, because you don't explicitly have to think about the stack if you do that, right? So it's kind of built into the structure of the recursion.
Okay.
So the reason we implemented explicitly is that with graph traversal, you can actually just like swap the stack for a queue and get breadth first rather than depth first.
Okay. Also, so sorry. I have one like final question. And it was actually in like question 6 and 7 as well.
Okay.
But if you go down to like the part where you start implementing DFS using like a stack, yeah, like
Okay.
right there. I get up till like when you created your stack, you appended everything to your stack. Like yeah, no, right there. Like if you
Yeah.
go down a little bit,
Yeah.
you found what like next position like ready. That made sense. But what is the results append for? And then I don't quite get everything after that.
Correct. So what we're doing, let me just reread it as well. So what we're doing here is we're saying if next position does not already have an answer, so we have not explored it yet, then add it to the stack. So the stack is like to be explored, right?
Yes.
So here we're saying if so we're saying, okay, like the other possibility is we already know what's going to happen with next pause, right? So in
Hmm.
that case, what we say is, okay, that's been explored. So that means that if so this is like true or false, basically, like whether you win or lose, right? So we're saying if this information already exists, then just write down that this move is going to result in this outcome.
Okay, cool. Got it. And then like when you go to okay, wait, no, that makes sense. And then the rest is like when you're just trying to find what the minimum number of moves are, you're like seeing that if it's your turn or if that type of, I guess, winning algorithm already occurs in results, then you like go up by one until you reach 21. And then using that, you find out wait, if you're gonna win or not, or like what's the minimum way you can win.
Sounds sounds kind of right. So what we want to know is what we want to know is whether we are like in a winning position, and by default we're not. And then we're saying if uh if we are not if we not wait, where did I get? Yeah. So what we want to know is like if the opponent is not winning with any of the possible moves, then we are winning, right? So is winning is keeping track of whether we found a situation where the opponent is not winning, right? So in all the results, so this is like in all the outcomes from the possible moves, we're asking what is there a winning move, and if there is a winning move, which move corresponds to the smallest possible number of moves.
Okay.
So after we are done with this, min move. So if his winning is true, then min moves is going to be the minimum number of moves that's going to result in us winning. Meaning,
So is the idea basically that like you have you, but then you also have like a computer that's gonna play, and so you're tracking your move, but then you're also saying like these are the possible moves like a computer or someone else can do, and then based off of that, these are the moves that you can do to optimize? Like, is it kind of predicting?
so kind of, right? So the way results works is we're just saying like if I'm in this position, am I winning or losing? So this is like if, right?
So then this is like this is a combination of dynamic programming and DFS. Like for each number or each number that you're at, what is like the best
Yeah, well, so
move?
like I think it's like dynamic programming only just in the sense that what we're doing is we're kind of like exploring this graph, but this graph has information that we're computing on the fly, right? So like we are trying to get from 0 to 21, but also like if we're at 1, we need to somehow keep track whether it's like me that's at 1 or you that's at 1. Right.
Okay.
And then in addition, we also need to like assign labels to like is one a winning position or is one a losing position. So it's dynamic programming in that sense. So it's DFS in the sense that the order in which we're exploring these positions is depth first.
Okay, I think that makes sense. Okay. Yeah, that was kind of all my questions, but thank you so much. That was really helpful.
Cool, no problem.
I'll see you later.
Okay, good luck.
Have a good day.